course, I would like to thank the organizer for the visit. It was my first visit to the Bayern, and I enjoyed it very much. So, for very well organized things. So, the written from the so, I'm going to discuss this. Something which describes both the temperature and velocity of an incompressible fluid. So, first of all, we start to look at torus. I'll explain in a moment. So, I believe the video is always periodic boundary conditions. And now I'm talking the the right-hand side theta, which is the temperature of the fluid, occurs, and it only acts in the vertical direction. Right? So it has the temperature as an influence. The second equation describes here the time evolution of the temperature. So you see it's very much alike the previous equation. So here nu is its final equation. Kappa, that's called the thermal again, very linear term. Of course, theta is a one-dimensional item, so you just take the inner product between u and grad of theta. So temperature acts on velocity, velocity acts on time. And you have both bilinear terms which look very much alike. Right, so, of course, my temperature will be a two-dimensional field, my velocity will be two-dimensional, temperature will be one-dimensional. I have initial conditions which I'm going to denote by u0 and u0. And as I mentioned before, I have the torus with periodic boundary conditions. Okay. So let me just give the notation that I'm going to use before. So whenever you see double bars, it means that this is a two-dimensional guy. So LP double bar P, that means pairs of LP functions. Zero, that's standard. Projecting that as pressure. So V0 is going to denote the square of square integrable functions which are divergence free on the domain. Pi is a Lorer projection. So the Stokes operator, strictly speaking, that's not delta, it's minus pi delta. And Vk with double bar will denote the domain of AK. And again, double bar means two-dimensional business. All right, now I want to try to have similar notations for the temperature. So everything will be tilde and these are double bars. So A tilde will be minus delta, HK will be. Then, of course, in this business, very important inequality, that's the Gagliardoni-Rosenberg inequality, which tells you in dimension 2 that H1 is included in any LP space provided that P is strictly finite, and gives you an upper bound of the LP norm of U in terms of a mixture between H1 and L2 norms. Of course, it's stated for pairs of functions, but it's exactly the same holds for just. Okay. Now, let me just give a few ideas of what's going for the linear term. So I think many of you, most of you, or all of you know what's going on for the linear term for the Navier equations. So you have a something going from V1 to V1 to V1, which is the dual space of V1, and it's defined in terms of this function of three functions. So you take V1 grad V2, you take in a product with U3. This makes sense provided that all three functions belong to V1. And then you give a name to this function of U1 and U2 so that the duality between V1, U2, and U3 is equal to this V lowercase U1, U2, U3. So if you want to express it, it's a Dore projection because here I'm taking V1, that means I'm taking either the three fields of the inner product U grad. Okay, because it's an incompressible fluid, I know that it's a very important property. If I exchange here U2 and U3, I get a minus sign, which of course means that if U2 matches U3 equals 0, which is extremely handy for technical reasons. But the reason why I'm working on a torus is that I'm going to need to raise regularity by one step. So in fact, I'm going to need to see what's going on for a to the 1/2 b of d, a to the 1/2 u by integration by part, which is this quantity. And because I'm taking a torus with boundary condition, parity boundary conditions, this vanishes as well. Okay, now what's going on for the bilinear term, which mixes temperature and velocity? This bilinear term, the second bilinear term, which appears in the PD that describes the time evolution of the temperature. So here it is. So again, if you exchange theta 1 and theta 2, you get a minus sign. So business as usual. But we'll see in a moment that, so of course, and if theta 1 is equal to theta 2, this vanishes, which to some extent allows you to treat the second equation just as the first one, kind of. But we'll see in a moment that if you raise regularity, then things are not as good anymore. So despite the fact that you are on the torus, you cannot hope that u grad theta a tilde theta does not vanish. So that's created the problems. Okay, now of course I'm going to, it's an SPD seminar workshop, so I'm going to introduce some stochastic perturbation. I'll deal with multiplicative noise, and it will be driven by independent Brownian motion. That I'm going to do W for the velocity and W tilde. Everything is tilde is related to the. So it's business as usual. W2 is a k-value Brownian motion with trace class covariance. Temperature is good. Temperature is perturbed by multiplicative noise driven by W tilde, which is another Brownian motion, which is independent of the first one with Christoph noise, which means that you can have these expansions of both infinite dimensional Brownian motions on K and K. All right, now I project everything on divergence-free fields, and now my new equation, the two sets of SPDs I'm going to deal with, will be exactly the same. That's the Navier-Stokes equation in the left-hand side. I've got rid of the pressure because I've been projecting on divergence-free fields. Now I'm projecting this again on divergence-free fields, and now I'm adding here a term, multiplicative term, driven by W, and here with some diffusion coefficient I'm going to explain in a moment which kind of assumptions are imposed. And something similar for the temperature. Okay. Now, what are the assumptions on diffusion coefficients? So, in fact, I will have two sets of assumptions. The first one is kind of natural. I'm just requiring that since I started with true Brownian motion on K, I'm just going to suppose that I have linear function in G of U will be linear from K to V0, and I'm imposing both conditions, which are at most linear growth and globally Lipschitz conditions. So that's kind of the expected. And here I start from L2 to L2, right? But for technical reasons, because I want to look at rates of convergence, I'll have to raise regularity by one step. That means that not only will I have to impose some linear growth conditions start from V0 and V0 here, but exactly the same kind of assumptions starting from V1 and going to V1. Okay. All right, and now for the temperature, I'm just going to mimic everything. So the second diffusion coefficient tilde goes from L2 to L2. Linear growth, global Lipschitz, and again, because of raising regularity by one step, I also have to impose some at most linear growth condition for the G of U whenever U belongs to each one. Now, of course, I want to discretize some things. This better exists. So the first result is the global robustness result. So here you need to impose what's going on from L2 to L2, both for temperature and velocity. So you get the existence of a unique solution. What do I mean by a solution? That's a weak solution, which means that here I'm taking in a product here with something which is in V1, a function phi which is in V1 for the velocity and in H1 for the temperature. And I write my equation taking inner products everywhere, or duality of everywhere. The solution is a unique, so there exists a unique pathwise solution, which is continuous, taking value into 0 and square integrable in time taking value into 1, both for velocity and temperature. Here, I mean, we could have some much more original results. We could impose that there could be some gradient inside of the diffusion coefficient that would not harm anything. But later on, we'll have to be more cautious. All right, that's good to have existence of uniqueness, but we also need moments. So,
excuse me, why do you have a p equal to 1 or p larger than or equal to 2? In between 1 and 2, for the p for integrability.
It is because I'm first using Hölder's Ito's formula for the square, right? And then once I've used Ito's formula for the square, I use again Ito's formula for x to the p, and if I want it to be C2, that's why I have this restriction of p. But of course, you are right, it's kind of silly to put it this way, because by interpolation, by Hölder's inequality, it should be any p. Yeah, you are right. Okay. So I have moments. So these moments, if I stick to H2, they are uniformly in time. And here there is a mixture between the H1 and the L2 norms, but we cannot hope for more, because I mean the Stokes operator doesn't put that. So uniformly in time, the L2 norm is bounded as all moments you like, provided that the initial conditions has these moments, and exactly the same property holds for the temperature. So this is a known result. I mean, it was, I guess, first proven in a joint paper with Xinxiao Duan long ago. Then we refined it with Shuishoff in a much more general setting, with more general assumptions on the diffusion. But again, the problem is that I will need to raise regularity by one step. It's not going to be good enough to have a controlled uniform time for the L2 norms of both temperature and velocity. I will have to have an H1. So the first result is that provided that your initial condition here now is in V1 with L2p moments, U0 and V0. So U0, I want to increase regularity for the velocity. So I just require that the initial condition lies in V1 with appropriate moments. But theta 0, as usual, can remain L2. Then I now suppose that my G coefficient, the one which acts on the velocity, is well behaved both in L2 and in H1. But for the temperature doesn't matter. L2 is good enough. Then almost surely my velocity is going to be taking value in H1. It's going to double in time taking value in V2. And uniformly in time, I'll be able to have bounds on the 2p bounds if I start with a 2p. Okay, so that's very good. And here, of course, I just look at the L2. So why is difference between two? I'm just going to focus on the bilinear term because the other term is kind of easy. So, as I mentioned, I want to get rid of the bilinear term because I have a periodic boundary condition and therefore this equality. And then, of course, in the problem which arises is that in the right-hand side of the time evolution equation, which describes the velocity, the temperature shows up, right? So how shall I deal with that? Well, it's very easy. You are encountering this term, right? You are looking at Ito's formula to the V0 norm of a to the 1/2 u. So this shows up. Then here you just use integration by parts. You put the a to the 1/2 on u. And because of the regularizing effect of the Stokes operator, you can get rid of that using Cauchy-Schwarz and Young's inequality with a small multiple here of AU of S, of the L2 norm of AU of S, and a large multiple of that. And since you know that uniformly on time, your temperature in L2 is bounded, that's fine. And then you just compute using Grandma's lemma. So here, that's why you can have different kind of assumptions on both sides. And it's absolutely crucial here to get rid of the bilinear term. Okay, now that's very good, but we'll have to have, unfortunately, both temperature and velocity will have to be there in kind of a similar way. So we have got to prove the same thing for the temperature. And here the disaster occurs, namely that here is so one has to first do something about it. And okay, the price to pay, so it's a bit ridiculous assumption, I suppose, but we were not able to do anything except if we are here require more integrability on both U0 and V0. Of course, if they are constant, if they are deterministic, you don't care. So it's not that serious, I suppose, if I start with deterministic initial conditions. Now, I suppose that both coefficients with required velocity and temperature are well behaved both in L2 and H1 norm. And we can prove that uniformly on time, the H1 norm of the temperature is well behaved, and that here some mixture between H2 and H1 norm is well behaved as well. That's, of course, that's more tricky because the bilinear term survives, and in fact, if time allows, okay, we'll see. I'll try to give you an idea of how the proof is going. Let me just say, roughly speaking, that there are two steps in the proof. In the first step, we prove that the supremum of expected value is fine, and this is used. This proof relies on the fact that we have been able to control the velocity uniformly in time in V1. Relies on the previous theorem I stated. And eventually, once we have proved that the supremum of the expected value of any exponent is finite, we can go and put the supremum in. So there are two steps in. It's quite technical. All right. Now, I want to get a strong rate of convergence. As you might suspect, everything will be based on a control of moments of increments in time. So what's going on if I take two time, tau1 and tau2, they are not stopping time, and they are just deterministic times. Between 0 and capital T. I look at the L2 norm of the increment U of T1, U of T2 minus U of T1, I raise it to the P, and I get, here I have to divide the exponent by 2, that's kind of to be expected because I have Brownian motion. So, but I just want to attract your attention on one point. Here I'm controlling the L2 norm, and I started with an initial condition which is more regular. I asked my initial condition to be in H1. And the reason why is that the term which involves the initial condition, if I write it in the mild form, the term which involves the initial condition will be well behaved, but not too close to 0. In front of this T1 minus T2, there will be some coefficient that's going to explode if T approaches 0. And this blow-up phenomenon disappears if I start here with an initial condition, which is in V1. Okay, exactly the same is true for now time increment of the temperature. So here, for the first step, because of this linear effect of theta, which I described when I kind of very sketchy proof of the control of moments of velocity, I can start with an initial temperature which is only in theta 0. If I want to get time increments of the velocity, if I want to get to describe time increments of the temperature, I have to ask for regularity for the temperature. Okay, so that's very good. I have a very nice control of time increments in the L2 norms, both for velocity and temperature. But again, I will have to raise regularity by one step, and that's not going to be good enough. I also need to control what's going on for time increments in the H1 norm. But there, in fact, what the good news is that we can stick with the same regularity of the initial conditions because this more refined norm, this more singular norm, will only appear in time inside of time interval. So in fact, the second result we have, that's of course it's tailored for time approximation. We take some uniform time mesh T over capital N for some strictly positive N. Tk is going to be the case time interval on the time grid. And we start again with U0, which is in V1, theta 0, which is in H2. And now what's going on here? So I'm looking at what's going on a small time interval, Tj minus 1 Tj. I take any point that runs in this time interval, and I compare U of S either with U of Tj, at the point of Tj, or U of S with U of Tj minus 1, at the starting point of this time interval. I square, I integrate in time on this small interval. I add all these small time intervals. I raise to the p and hope that when I take expected value, everything is well behaved. And that's the case. The only bad news, but it's not so bad news, is that here I lose a b. instead of having here t over n to the p, which I might have obtained here, I have t over n to the eta p, and eta is strictly between 1, but of course that's close to 1 as I. Okay, so this is the first thing for velocity. Now it comes to temperature, then you see that again, assumptions are deteriorating because of the fact that the beginner term is not vanishing as I would like. But basically it's the same thing. You compare theta of s either with theta of the upper bound or the lower bound of the integral, you square, you add to the p, take expected value, and this is nicely bounded. Okay. So now that I have my hands on what's going on for moments of time increments, I can hope to describe the scheme and hope the best as far as speed of conversion, rate of convergence is concerned. So let me describe a semi-implicit Euler scheme. So I have my constant time mesh t over n. I'm going to describe simultaneously the scheme for temperature, the velocity, and the scheme for the temperature. And it's kind of business as usual, so it's semi-implicit because here I'm looking at the increment uj minus un minus 1, and here I require un because of stability issues. I have to take it implicit in this place. And here it's semi-implicit because in the beginner term I'm mixing un minus 1, which I know, and un, which is my unknown. Right? So that means that here this equation is going to be linear in un. And in the right-hand side, I put my name that maybe zeta minus. And of course, in the stochastic term, because of the species, I still use un. Of course, I did not mention, but I guess that's kind of obvious. I start my scheme at the initial conditions u0 and theta 0. And here it's exactly the same idea for the scheme that describes the temperature. Again, it's implicit here. And here again, it's semi-implicit because in the bilinear term, I'm mixing what I already know, un minus 1, with my unknown. Okay, so the question which arises is, does this exist? Is it nice? Does it have good moments? And the answer is yes. Existence of the scheme is a kind of standard procedure. You look at an approximation, you project on finite dimensional subset, you use our theorem, that means you have some fixed point, you pass to the limit, you identify the limit, and everything is well behaved. So the proof is exactly similar to what Kareli and Paul did in their very first paper on the rate of convergence for the Navier-Stokes equations for the. And the good news is that thanks to the regularizing effect of A, as of line 1, both schemes will belong to each one. So let me also describe a fully implicit scheme. You put bars on it, it's just the same, except that here I'm starting with a linear term, which is u bar L u bar. But otherwise, I can do exactly what I did previously. And strangely enough, including in previous paper I wrote with Hakima, people are usually focusing on this fully implicit scheme, which is kind of ridiculous because, I mean, the semi-implicit one is just as well behaved. So again, if I look at the fully implicit scheme, there is uniqueness. And because all the results I'm going to present further are exactly the same for whether you look at the fully or the semi-implicit scheme, I just forget about the bars and call my schemes UL and theta. Okay. So my scheme exists. Is it well behaved as far as moments are concerned? The answer is yes. It is well behaved, except that here, because of technical reason, if you want to prove that any moment of P is well behaved, you use an induction argument of the exponent of 2. That's just technical issue. So that's why the initial conditions are here stated in terms of dyadic exponents. So suppose that you have enough integrability on u0, enough integrability on theta 0, then uniformly on the boundary, your H0 moments, both for temperature and velocity, are going to be well behaved. And here you just try to mimic the time interval you had in the previous results from control of moments of velocity and temperature in H2, N2, sorry, and you get this. So the proof is, again, an induction argument of the exponent of U0, and it just mimics what was done by Boussinesq. All right. Now, rate of convergence. So I now have my scheme, I have my functions, my processes, and let me denote by Ej the error term U of Tj minus Uj, and it has still the J, the error term between zeta of Tj and of course my initial error terms are 0 because I started with the initial conditions. And again now you are going to laugh, or maybe not, because I again have to raise integrability multiplied by 2. So provided that my integral conditions are evaluating V1 and H1 respectively, I have a rate of convergence in probability, which is, let's say, almost a half. So what do I mean by that? I look at the maximum, so this notion of rate of convergence in probability, I think it was introduced by Jacques Printemps very long ago. And Arnaud, do you think it was earlier, or it's Jacques? I think it's Jacques who introduced it. So, so here you look at the probability that, on one hand, the maximum of the L2 norms of your error terms, and on the other hand, here some kind of time integral kind of the H1 norm exceeds some bound. This bound, of course, has got to go to 0, and the rate is going to be eta. And you want that the probability that this term misbehaves, namely is larger than n to the minus eta, goes to 0. In that case, we'll say that the rate of convergence is eta in probability. I believe that, so we were able to prove that, provided that it is strictly less than 1, which means that we got a rate of convergence of probability, which is almost a half. I believe that this is the best we can do with these kind of assumptions on our initial conditions. Now, let me mention the fact that Brett and Paul proved the rate almost 1, but they had to impose more regularity on the initial condition and more regularity on the noise, and I think it was only in the additive case. So, to the best of my knowledge, with the kind of assumptions we have almost a half, and we are happy about it. All right, that's rate of convergence in probability. Now, I would like to see what's going on for the L2, for the strong rate of convergence, and then it's not as good. So, the rate of convergence in L2 omega, you just take any to the q, but q is larger than or equal to 5, so 32 is good enough. Then you will get exactly the same quantity as before, except that this time you want to look at the expected value of this guy. And you hope that it's going to go to 0 in a polynomial way. But unfortunately, with a purely additive multiplicative noise, we are only able to prove that it goes to 0 as inverse of logarithm to some exponent. And of course, it's a bit strange because if you start with deterministic initial conditions, then Q is arbitrary, right? So you get an arbitrary decay of logarithm, which means that there is something on the line that we are not doing properly. I would like to get a polynomial rate of convergence. At the very end, I'm going to mention some results, results. I think in the additive case, we can have polynomial rate of convergence. Okay, so this is similar to what we obtained for the two stochastic two-Navier-Stokes equation in the multiplicative case, and again, it's kind of ridiculous result because you get any negative exponent of logarithm, which means that you are missing something. Okay, let me try to explain how we can get these rates of convergence. So the crux of the matter in the multiplicative case is going to localize. We prove from localized convergence, and here we just follow the scheme of proof that Carly and Paul did in their very first paper. So we are localizing on uniformly on time control of the H1 norm on both temperature and velocity. Omega m is a set where this is well behaved, and namely it's upper estimated by m. And then we look back at their two conversions, except that here we insert the integrated function of this good set, where everything is well behaved. And in the right-hand side, we obtain t to the n to the eta tilde for any eta tilde in between 0 and 1. That's fine, except that Bad news is that here, inside of this exponential term, which is come, of course, from my schema, this constant n is showing up. 1 plus n in front, that's not very serious. But the fact that here inside you have, inside of the exponential, you have n is bad news. A constant c tilde can be described explicitly, but it doesn't really matter. It's okay, so the bad news is that here we have this exponential term. All right, but at least we can see what's going on in the good set, where uniformly in time is one more time. So if we want to deduce from that the rate of convergence in probability, look at the set n eta, where we, here we want to control, what we want to prove is that the probability of this set goes to 0 as n goes to infinity. Of course, the idea is going to choose m, this truncation business, appropriately according to n, right? We have to hook up some m of n, and we are going to split what's going on for that set, depending on the fact that everything is controlled by m of n, or everything is out of reach. Okay, so you have this upper estimate, and it's just, the game is just to find m of n. So here you start with m of n, which is log n. It does go to infinity very slowly, but it does go to infinity, right? Then you can get upper bounds. So on the set where you can control everything in terms of m of n, you just use Markov's inequality, and you end up with this term. But of course, you have log to some exponent, and n to the minus eta tilde plus eta. So if you want to avoid eta, you just insert some eta tilde in between eta and 1, and you are done. Because of course, in this competition, it's this term which wins. So this goes to 0. And because we have good moments for uniformly in time for the H1 norm, both for velocity and temperature, we know that the bad set is always well behaved, because m of n goes to infinity and this will be found. So rate of convergence in probability is very easy to deduce from this localized convergence result we have. All right, now if we want to have the strong rate of convergence in the multiplicative case, then things are not as good, because now we have to deal with moments. So we have 2 to the q moments of the scheme. We have any moments we like for the function, for the processes. So let's take p and 2 to the q to be conjugate exponents. And here we are going to have to see what's going on if we localize now on the bad set. So on the bad set, because this quantity has all moments you like, you use Euler's inequality, and you end up with some constant multiplied by the probability of the bad set. Okay, now how can you approximate the probability? Well, that's Markov's inequality. Very good. You end up with that. All right, and now the idea is going to match, to find a good m of n that's going to match what's going on the good set and what's going on the bad set, right? So you take logarithm, and you end up with this equation. This is what is, if I take the logarithm, what's going on here, and this is what's going on here, because here I lose a little bit because I have to take the 1 over q. All right. So you are facing this equality. It's a mixture of logarithm of m and m of n, and you think, okay, let's take m of n of the order of logarithm of n. So you start with m of n in this form. We write explicitly in terms of logarithm of n. And that means that approximately it's only this term which matters, right? So you get something which is up to some constant logarithm of n. Then you are happy because the both terms you have to control are equal up to some constant. And then you plug in. And when you plug in, unfortunately, you get some exponent, negative exponent of logarithm, but not more than that, right? Okay, so I guess I have 5 minutes.
Yeah.
Okay. So I can give you a big idea of how we prove moments of uniformly in time for the temperature, because that's more tricky. So as I mentioned, the first step, okay, for technical reasons, we take some stopping time where everything is going to be bounded, because at the end of the day we have to do one myself. But here we put the important thing is that we put the Fremont time outside. So what we want is to prove. And then the proof relies on something which has been mentioned by Euler in this talk, is a paper by Giga Mikayawa, which gives, I think it was just maybe a paper before the one you mentioned, where they give upper bounds of any negative exponent of the Laplace operator, acting not any because there are constraints, acting on the Billinout term. They do not formulate it in terms of mixture of temperature and velocity, they only mention it for the velocity. So the L2 norm of this Billinout term can be upper-estimated by positive exponents of a to the alpha u, L2 norm, and here a tilde rho, L2 norm. And there are some constraints between these three guys. On one hand, you want that delta plus rho is strictly larger than a half, and that the sum of all three exponents be larger than or equal to 1. Okay, then you are facing these norms, and of course, by interpolation, you can upper-estimate it in terms, provided that A and rho both are less than a half. You can upper-estimate these two norms in terms of A to the 1/2 norm of u to some exponent, and norm of u to some other exponent, to do both for temperature and velocity, and then you end up with constant alpha. So the Billinout term, the nasty term which doesn't want to vanish, is going to, and here I'm looking at the mild formulation. This nasty term is upper-estimated by some t to the minus t minus s to the minus 1 plus beta, but beta is strictly positive, multiplied by what you would like here. It should be or multiplied by something you can put your hands on, because uniformly in time, here you get the H1 norm of the velocity, but here you only have the L2 norm of the temperature. And L2 norm of the temperature, you know how to deal with uniformly in time. So what you have put outside of the time integral is fine. And what's going on that here you get t minus an exponent of t minus s, or a convolution with an exponent which is strictly less than 1. And then you use a refined version of Convergence lemma, which tells you that whenever you have a function which is bounded, that's why we have this stopping time, which satisfies this equation, this upper bound. So it's a constant plus some time integral with here some an exponent which is strictly larger than 1, plus even a constant if you like. And uniformly on time, you can upper bound this function. So that enables you to prove what's going on for the supremum outside. Then we go to Ito's formula, we go to the weak formulation, and we again use Gagliardo-Nyrén, no, not again, I'm sorry, we use Gagliardo-Nyrén inequality. Here we just do our best here to use again the fact that this upper bound is this upper bound is this term. Then we have this kind of exponents. And then you are facing here something which only has 3/4 exponent, strictly less than 2. Convergence inequality. Convergence inequality and Young's inequality. You end up with the control of this bad term, which is upper-estimated in terms of here, something that it's a mixture of something which appears in the left-hand side because of the regularizing effect of the Laplace operator. And here the extra term is going to be the supremum of the V1 norm. For the velocity, that's fine, multiplied by this integral. And since you know how to control things with supremum of t outside of the expected value, you can put your hands on. And in the last 2 minutes, let me just present some further work in progress at the first item. So I prefer not to present it today because it still has to be double-checked and polished, but we know, I think, that using exponential moments of various norms of velocity and temperature, and we can prove a strong polynomial rate of convergence. That means that the expected value of the supremum of the square of the L2 norm is going to be upper bounded by some power of the we can only deduce that in the L2 norm for the velocity, and we have got to require that the norm is static. Because here we no longer use the logaritic result, violating this omega by omega arguments, the reason why is that in the purely additive case, there is no, the term which in motion vanishes. Omega by omega. Okay, then of course, as I mentioned, for technical reasons, we have to increase exponents as we go on for the temperature, which is a bit unpleasant. So we would like to get rid of these kind of strange assumptions we had raising exponents. Well, we would like to prove exponential moments uniform in time for the H1 norm of the temperature, but this might be out of reach. I don't know. That would enable us to get polynomial rate of convergence for the air term for the temperature. And then, of course, we would like to get rid of this assumption that it's a torus with periodic boundary conditions. Use study space-time approximation, as Brett and Paul did. If we increase regularity of the initial condition, if we increase regularity of the noise, and we still have we might have differential convergence in probability. And okay, maybe also Brett and Paul introduced the notion of non-strong solutions, and they dealt with convergence in probability. And of course, here what we have done is looking at a very particular NR model that mixes temperature and velocity for an incompressible fluid. The more general NR problem is with 3 items: velocity, temperature, and magnetic field. But I mean, the bilinear terms are more nasty, so maybe might be some further ones. Okay. Thank you very much.